I'd like to first of all welcome you to my talk. Thanks for being here. I'd like to thank particularly Nick Smith for inviting me to talk about his work. And here it is, so I can go present it. The work I'm going to present is actually close collaborative work with Dan Beard, with whom we decided to go try test his models in the skeletal muscle behavior environment, and I'll tell you a little bit why I'm doing this. So this is the big picture, zooming in on this part. And then within this model that Peter Hunt and Paul Nielsen reviewed, there's this compartment here, which is the mitochondrion, and this particular one, which is the glycogenolytic pathway. These are two major metabolic pathways. So in order to have this kind of models run, we need to be able to first test what kind of detailed knowledge we need, and hopefully then condense it so it can run within the bigger framework of the whole organism. So in this talk, I'm going to focus, also because of time constraints, on the mitochondrial model testing that we've been doing. Basically, we take Dan's model that he published in PLOS in 2005. Most of you probably know it. It's got these kind of components. There's no calcium signaling in this mitochondrial version yet, this generation. There's some lists and there's some typical examples of the kind of rate equations that Dan's developed. In my talk, I'm going to focus on this particular type, where this is the reaction turning ATP into ADP. It's probably hard to see. And then this is being fed back into the heart, into the mitochondrion, and stimulating F1 ATP synthase to get energy balance. So why are we doing this in the skeletal muscle? Well, one really nice feature of muscle, it's got a 500-fold dynamic range of ATP metabolism. As you're sitting here, you're turning over about 0.01 millimolars of ATP per second, and if you're running at max when you're chased by a lion, you can crank it up 500-fold. It's easily controlled, it's an easy function readout, we've got a lot of it, it's on the surface so we can measure it easily, and this would of course not work unless the mitochondrial and glycogenolytic pathways would be to a large extent homologous in cardiac and skeletal muscle, and there's some good data on that. So this is why we're taking this. Well, our test data, so we move from the in vitro single cell and multiple cell things, we go to the in vivo system of the integrated, and we use NMR. Well, most of you typically know these kind of images. So this is somebody's got a forearm crammed into a 2 Tesla NMR scanner, and if you take an image, you would see some bones, some subcutaneous fat, and some gray muscle, and some holes where the blood's flowing. Now you can also get the NMR spectra, and if you take a spectrum where you're looking at all the phosphate-containing metabolites, what is really nice is that we get signals non-invasively from these metabolites. And the chemical shift difference between these two resonances gives direct information on a 2-digit level of information on intercellular pH. And Richard Von Jones showed us this morning how important that is. So that's made NMR a really powerful method to investigate cell energetics, because if this is the metabolic network that we're typically interrogating, these three we can directly observe with NMR, and this one, ADP, we can compute when we have the creatine kinase information and we know the pH. So then we can compute the free energy of this system. More importantly, you can do dynamic measurements. So here you see a resting muscle, then you start stimulating it simply by electrically or using your fingers, and then you see phosphocreatine being turned into PI, buffering ATP. ATP levels are constant. You stop exercise, you get a resynthesis of phosphocreatine, PI is being built into ATP, and this rate gives you information on how fast your mitochondria are working if glycogenolysis is going at a low rate. So this has been also massively been applied in clinical studies. So you can get this kind of very quantitative information where this is flux. You can compute from these kind of measurements at steady state. You can compute as a function of twitch frequency what the flux of ATP production by the mitochondria is, and indirectly from the proton change you can make an estimate of what the glycogenolytic rate has been. So fluxes, quantitative numbers, ideal for the kind of test that we're interested in. More recently, we've got a bicycle ergometer, so inside our scanner, we can actually do bicycle work. So we can go to really high workloads. For sake of time, I'm not going to show you how it looks, but it's pretty darn cool. And what's really important is that here, this is the muscle at rest, and you can see that we can turn PCR pretty much into an organic phosphate. This person is going at a heart rate of 180. He's completely maxed out. ATP is still constant, as you can see, at least in the bulk of the mass that we're observing. And what we found really exciting to identify is that there's another resonance that we can now observe. So this appears during exercise, and the moment you stop and you have rebuilt your phosphocreatine pool, you can now see this thing still being there. And this is phosphorylated glucose, which has got a lot of energy. It's about 9 millimolars, and it's just sitting there. The muscle apparently doesn't need it. So this is really also added being able to observe these concentration changes in this network when you're going at these very high workloads that you're doing when you're doing all-out bicycling exercise. Now here's some pooled results of these phosphorylated glucose dynamics. So here's at rest, and then it's pretty flat, and then at this third workload, it really starts going up when you start activating your fast glycolytic fibers. And then what's interesting, it pretty much peaks after exercise, and then it sits there. So, well, this is the best available model for glycogenolysis in muscle around. So when we fed these dynamics to the model, that was a nice way to test how accurate this is for in vivo conditions. So here's our data set, and unfortunately, it's not a very good model because it predicted that within about 400 seconds, this should all be gone. Whereas in real life, it takes about 15 minutes before this is turned over. So clearly, the controls of glycogenolysis, we don't know too much about in our models yet. So my student Joep Smeets has got a poster on work that he did for his master thesis, trying to improve this. And we've made some progress, but it's still all quite hypothetical. But back to the Beard mitochondrial model that's also Edmund Crampon is using in his ischemia studies. Now, when Dan published his 2006 paper where he took some Bob Balaban data, which is steady state NMR observations, NMR is quite insensitive, so you have to time average over seconds at least. And this is what he found, that these are the data showing as a function, if you increase your oxygen consumption, so the ATP turnover rate, and you look at the relative ADP signal or the phosphocreatine concentration, it's pretty much flat over this range. This is a very small range. And it predicted if it would go further up, it would increase. But it's really hard to get your heart up right there. So that's when Dan and I, we published it in 2006. We added the skeletal muscle. So Dan converted it by volume changes, not much else, for skeletal muscle. And this solid line is the prediction of the model again, and this is the steady state data that we got from NMR. PI data is pretty scattered compared to ADP, and the estimation of the resting state is quite off. Dan and I are not so happy about that. But other than that, there seems to be some agreement. But this is all steady state, right? In the heart, of course, like a bicycling human, we're doing pulsatile work. So we need to be able to, to have it be useful for the kind of questions that you're asking, it needs to be able to also predict dynamic data. And unfortunately, what we found is this is some data from the exercise where we rapidly deplete phosphocreatine, and then this analysis is fitted for this resynthesis rate. Dan's model predicted that it would drop much more during the exercise. So there is some disagreement there. Okay, it doesn't fall flat on its face. So Dan's model is homeostatic, it's just not quick enough. So we concluded from that the flux regulation is off. Okay, it's not bad, it's just off, and we need to find out more if we can, if we want to use it for the dynamics. So for that, if you look at the flux regulation built into Dan's model, it is feedback. So ATP is being turned into ADP and PI, and it's being feedback via the transporter to F1 ATPase and ADP by the exchanger to there. So we're focusing on this particular. So what do we know about this sensing? Well, in '96, we found also in vivo, but also if you take old in vitro data from mitochondria, that you look at the relation between rate and scaled ADP sensitivity to the Km, you find that this function is actually a second order function. And the model that we used when Van analyzed the sensitivity, this is first order. So there's a factor of 10 difference in ADP sensitivity. Okay, so it's off. So we have an important question now. Is the model missing components, or is just the parameterization off? It will be the latter case, we're in good shape. Then we can still hopefully move on. If we need to add more components, that's going to be really tricky. So a way to go about this is that I collaborate with the biomodeling and informatics group in our bioengineering department in Eindhoven, and they're really good at analyzing models. So thus far we've seen many predictions of models. Here we're going to go through an analysis of the models. So what we do, and we can talk about this because of the lack of time, we generate multiple random sets of parameter values where we change them between 50 and 200%. And we add dummy parameters, and then we compute this function for each data set. We characterize it, and then we correlate the change for each parameter set to what these values are. And what we found, importantly, that these parameters are the ones that control the sensitivity. So it's a dehydrogenase parameter in the model and the A and T. So these parameters determine the sensitivity. So the good thing is we have information now that it's not all the parameters that may be adjusted, it's only these. So to move forward with this, we applied model fitting. So we got a really good data set from these high resolution NMR measurements, so we can sample this relation really well. So just as a default case, if we just simulate, there's no fitting, just compute it. For this is the measured rate for the subject, and these are the parameters that Van determined for the original value, so you can see it's far off. So if we just change these parameters, but not this theta, which is some thermodynamic parameter, what we find, we can improve it. So that's one solution. And we get indeed a Hill coefficient on the order of 2. And it's got a very high ADP affinity, which we know in vivo. The other option is fit just these two, also fit theta. And then we got this solution, also order of, about 2. So we have two solutions. Okay, that's why it's nice to have a model, because we can also look at some other parameters. So if you look at this potential, the NADH over NAD ratio, we know this is a crucial parameter. And for this particular parameterization, it predicts that if you activate it, it falls flat. And also the membrane potential for this one, it drops way below the physiological rates where you actually have apoptosis of your mitochondria. So we know this one can be right. So how about the other one? Well, if we look at the NADH over NAD ratio, it stays nicely and it's highly robustly buffered. So that was okay. Membrane potential, same thing. So the last thing, so have we just tinkered with a parameter, or did we actually learn something mechanistic? Well, actually this is the original formulation that Dan took from some previous model, where this theta is in these rate equations. And if you change it from 0.35 to 1, now you have a whole different A&T model. Okay, so wrapping up, if we go back to the bigger picture, we've made some progress, we hope, so that it can actually now be used to also predict and deal with transients. And in the even bigger picture, we hope it might benefit the very good work of this consortium. And I would like to end up with these acknowledgements, specifically Dan Beard and Joep Smeets, who did all this work for his master thesis. Thank you.
Thanks very much. Perhaps we could have one brief question over here.
Probably a near trivial question. What part of the body is actually being sampled when you have the whole bicycle ergometer and the NMR?
Well, we actually, I can show you later. We put the probe on the muscle, and so it's just being triggered every time it goes back in the same position in the magnet. We get a signal. So we get every 3 seconds we can get a shot.
I think we should